Hello, my name is Javier Stefan and this is Richard Gonzalez. This is our finger pulse project for medical instrumentation design.
In this experiment, we were tasked with constructing a finger pulse measuring device. Our device is incorporated using an infrared emitter along with a phototransistor receiver, which in turn will create an electrical output telling our 10 LED bar when to light up according to our pulse. In this experiment, we answered these two primary questions based on our circuit. We experimented to see if any of the surrounding light would affect our signal being created by the phototransistor receiver. We also experimented to see if when we placed different resistors in series with the phototransistor, how it would affect our signal's values. Absorption of electromagnetic radiation is defined as the way in which the energy of a photon is taken up by matter. The amount of energy in a light wave is related to its wavelength. The shorter wavelengths have more energy. Infrared light is split into three categories: near infrared, mid-infrared, and thermal infrared. Near infrared has the shortest wavelengths, making it best for this experiment. Photoplethysmography is an optical measurement of volume flow through a biological system. Plethysmography is a technology which uses light absorbance as a method to generate waveforms from the pulsating blood. In a reflection probe, the light-emitting sources are located adjacent to one another in the probe, and the photosensors capture the amount of light that diffracts from the skin. Transmission probes have photosensors on the opposite side of the light-emitting diodes. The light goes through the skin, and the light that comes out from the other end is the output, which is displayed as the wave. Capillaries are the body's smallest blood vessels. Their thickness varies anywhere from 5 to 10 micrometers in diameter. The capillaries are responsible for the exchange of water, oxygen, carbon dioxide, and other substances between the blood and tissues.
Here we see the schematic design for a finger pulse instrument. We use different types of components from a phototransistor to an infrared LED, op-amps, diodes, capacitors, and resistors. This picture demonstrates the transformation from a schematic to the actual breadboard, including the schematic from the LED bar. For our results, we see in Table 1, when we tested the phototransistor with the light on, we received lots of noise for the signal, because surrounding lights from the ceiling, computer screens, etc. were being collected through the phototransistor. When we turned off the lights in the room and all equipment with lights, the phototransistor was collecting about 4.89 volts with minimum noise. The second table demonstrates a simple experiment to test a phototransistor. We tested different resistors in parallel with the phototransistor to test which resistor is the best for the cardiac output. Results from table 2 demonstrate that 1 mega ohm resistor is the best option. Throughout this experiment, we made a few observations. During the circuit preparation, we learned that surrounding lights can affect the signal of the finger pulse, and in a hospital or clinic environment, false results can jeopardize a patient. We also observed during configuration 1 that an LED light isn't as powerful as an infrared light. Due to our observation, when building a sensor holder, to minimize surround lighting to cause noise in the signal, the LED and phototransistor should be covered with a black material, not allowing any type of light in. One of the main lessons learned in the lab was a post-transit time blood pressure monitor, in which the receiver and emitter were pointed at each other and the finger was placed in between them. Another lesson learned was how the light spectrum affects the results for the signal. We first tested with a standard red LED and then changed the LED to an infrared LED, and the signal was a lot stronger. We also learned the best way to collect the cardiac pulse from a human fingertip is placement of the finger between the phototransistor and the LED source. We first placed it between the nail and the opposite side of the finger to utilize the most light, but after research we noticed that it is best placed in the same plane of the finger to read the pulse of a human being.